Our next speaker is, of course, Dr. Luca Brocca, Director of Research at the National Research Council's Research Institute for Geo-Hydrological Protection in Italy. Another speaker making his symposium debut here, as well as Adam, albeit came a much shorter way. In his presentation today, he'll talk about the role of AI in developing and improving a digital twin for hydrology, where he'll showcase the digital twin on, or the next project on digital twins for hydrology. I've been also a personal fan of his during my graduate studies. He was, I think, one of the visionaries on reverse hydrology. So how do you compute atmospheric variables from surface variables? I think Adam alluded a little bit to that, so we'll get into a deeper dive with Luca today.
The last major consideration of Adam was probably fast accuracy and precision was probably the best way to start my presentation, because I fully agree. And also this morning we see in the plenary talk that I don't know, fantastic simulation of the Earth system with clouds, solid systems, everything. Before or later my slide will start, but I have the same impression. I have some nice video, but actually yes, the accuracy of our prediction are still. Should I press something or? Here we go. I think. Yes, this is me. Anybody has heard about the digital twin Earth in Europe? Many of us. Yes. Well, this is basically why many people recognize me in the past 3 or 4 years, because you know we always talk about keywords in our life, and digital twin Earth has become probably the keywords for myself. But let's start with the single slide, 2 slides for myself. This is my research career. I started in 2003, so in most from the institute data. Then I use a lot of satellite data with satellite with the model and with modeling and satellite observation to integrate them. And at the end, you can see the digital twin Earth hydrology. That is the current, basically, main project that we are running. So in most ways, the main things in my career. If you look at the satellite data, basically, who was born first? Yeah, the slide are cut. But so most of the data from satellites started in November 78. And actually, it was the same date, the same month in which I was born. And I have already looking at CELMOST. So basically, my career started since when I was born. Why flood prediction is important? Then few slides about the problem. The problem is that, for instance, this is a slide on Storm Daniel occurred in September 2023. With in Greece, we have 1,000 square kilometers of flooded area. Basically, hilly areas becomes like highlands. But the most impactful problem was in Libya, in which we have estimated, but probably more there, 10,000 casualties for a single flood event. Similar things occurred also in Italy. I will skip some of the slides to gain time, because I want just to give, but for instance here, in 15 days, it occurs more than 150 millimeters in 1 day. And exactly in the same area, as you can see in the middle here in the Emilia-Romagna region. And if you go to the other side of the coin, drought, this is the IPCC report, and basically the orange hexagon are the areas in which we have already observed increase in drought occurrence. And if you have dots inside, basically the confidence in human contribution is high. So for instance, the Mediterranean area is very high. And if you look at simulation for the Europe, on the y axis it is mean duration of drought. On the x-axis the mean area, so bigger is the bubble, worse is the problem. In 2018 to 20, we have the biggest bubble, so basically in the recent years. But if you look at the climate projection, basically this will be a good year. So we expect that in the future we are really going to experience water scarcity very, very, very often. And this is actually occurring already, because actually if you look at the last 5 years in Europe, in Central Europe, we have already experiencing a lot of drought events. What will you learn today? Yeah, what is the Digital Twin Earth Hydrology Project? Shortly. What are the more recent advances in satellite data? Actually, we are much confident now that satellite data can help a lot in improving our modeling, but still we are far from being there, at least for the land application. How to integrate satellite modeling is still challenging, and what are, at the end, what are the key challenges? In red, you will see the potential role of AI in my slides. This video basically shows why it's important, what is happening in the last 5 years. Basically, this is the land system. You can see precipitation, and on the ground you have evaporation. And basically, if you want to simulate the Earth system, you need the data at very high resolution. Since 5 years ago, from satellite, for instance, we can get precipitation monthly, 10 kilometer scale, 20 kilometer scale. Now we have data at the daily 1 kilometer scale, even sub-daily, even hourly, as actually we have seen also this morning. And so basically this data can help us a lot to basically provide improved simulation of the Earth system. And this is just an example that, for instance, the video is slower than I expected, but it should be faster. But in any case, before or later, it will happen that these data are going to be used, for instance, in Sicily, in which we had the big flood events in 2022, and this is, for instance, the simulation of flooded area. I will skip the video to save time. So what we have done this Digital Twin Hydrology project. If you are interested, basically we have two papers. This paper is for young minds, so if you are not expert in the field, basically reading this paper, you can get direct access to what we are doing. And if you are a bit more expert, there is also the big paper published last year, and I guess that the slides of the recording will be available, so basically you will have time to read them and also to get access to the data. And now what we have, the slides are cut for kind of 2 centimeters, but in any case, this is the Digital Twin Hydrology project now, in which basically they are involved more than 15 institutions in Europe, and now we are developing satellite data for Europe and Africa at high resolution, and we are going to use this data for many applications related to water, because basically hydrology is my main topic, and related to water means drought, flood, water management, and also landslide prediction. This project is not alone. Here in the middle you can see the websites, but basically why we are able to do a lot of things is that basically, I don't know, many people actually are working around this, but more or less we should be more than 100 people together that we are working together. But no, it's even more, because there are more probably 100 institutions. So, and that's why basically all these projects now are funded by European Commission, for instance, in the top, or EUMETSAT and NISA, that are the two main space agencies in Europe. And so basically all these projects goes together, and the Digital Twin Hydrology project is a kind of collector of all these initiatives. So for getting, for instance, high resolution precipitation or irrigation water use, the human impact is very important, or even future mission that can be explored in the future. For more information, educational material, you can go to the website. There is also an interactive web platform in which you can directly explore, and you can play around with the system that you are running, because actually the key points of the digital twin is that actually digital twin should be something that should be interactive, which means that basically people should be able to interact with the system directly. And here we have developed this platform to basically make the people to interact with the system, to make questions to the system, to create what-if scenario for what is going to happen in the future. And this is quite challenging. So what we have now, we have, for instance, high resolution thermometer from space. Europe has launched the Sentinel constellation. Sentinel-1 is probably the main sensor here. And if you look in the middle, it's a precipitation map. And you can see, in the middle is a soil monster map. And you can see on the right radar precipitation. And you can easily see that they are the same pattern. Basically, you can easily see the footprint of precipitation on the ground with Sentinel-1. It means that with Sentinel-1 data, basically, for the first time, we could be able to estimate precipitation at very high resolution, 1 kilometer scale, but even 100-meter resolution kilometer scale. This is another example of the footprint of precipitation over soil moisture data, the animation. And on the right, I love the time series plots. On the right, you can see the green is modeling, and the blue is satellite data, and you can see that there is a very, very nice agreement between the two. And so, for instance, we can get precipitation at very high resolution, and you can see in the animation, it's precipitation over time in northern Italy, and you can see that basically the pattern is very, very well simulated. AI has been used here from one of my colleagues that now is in CNWF. Basically, he developed an approach with AI to get high resolution from space. Basically, what we did in Northern Europe, now we are extending in for the whole Italy and also for the whole Europe and Africa. And uncertainty is something that we are basically, everybody is speaking about prediction, but the uncertainty around this prediction, around the observation, around satellite data are quite important. Most of the time, we are not aware of these uncertainties. We are started to look at this uncertainty in precipitation data. It's a complex issue, but this paper is one example of some precipitation estimates from space with the uncertainty untouched. And this is really very important, and AI can play a big role here. Precipitation data basically is the most used. Actually, also this morning you have seen a lot of slides with precipitation because actually everybody knows about precipitation. So basically there are a lot of papers that now they are going to use this high resolution precipitation data, but you can imagine that this data at 1 kilometer scale has been available since a couple of years. So it means that more is going to come in the near future. All the data are freely available. The other problem of open access data is really very important problem. Here, all the data are available in the QR code to explore the platform. So far, we have data only for the Mediterranean scale, but as I told you, basically, data will be available over and can be accessible to everybody for Europe and Africa very soon, very likely by the end of this year. Then what is the problem? How to integrate satellite data and modeling? This is the water cycle as probably everybody studied at the school. Very natural system with evaporation from the land, then runoff, and water river discharge goes back to the sea. But as also mentioned by my previous colleagues, the new water cycle is not new. Basically, the water cycle is always the same, but actually the human part of the system has become really huge. Just some numbers. We have 60,000 large dams in over the globe. Large dams means higher than 10 meters. But if you look at the small dams, for instance, just Italy, 26,000 small dams. If you look at the Po Valley, that is something that I'm studying a lot, 30% of precipitation is used for irrigation. On a global scale, irrigation is the major user of water. To model human impact on the water cycle is from very difficult to almost impossible, because actually we have to model human behavior. And if you, in all the systems that, for instance, irrigation is something that we are doing a lot, but if we predict the system as we did for physical model, that is a kind of optimistic, optimal way of managing water, this is not the case for farmer. And so this is a big issue, and if you want to basically predict the water cycle over human impacted system that are a lot of in the world, it's very, very challenging. And all the nice simulation that I have also shown to you are basically might be completely wrong. What we are doing basically we are improving our modeling system. For instance, we have used our modeling system by using satellite precipitation to predict flooding over more than 2,000 catchment around the globe. But we have to use the same model for also water management in human impacted system. It is not enough. We have improved our modeling system. Everything is open. Actually, you can access to the model here, and including the human impact. And what is the role? I have just one slide. What is the role real of satellite data? Typically in hydrology, our main topic is to get to the first line. First line is black is the model, green is the observation, and basically we always look at stimulating river discharge. But if our model should simulate all the water component of the water cycle, because we want to use the model for managing water, we also need to simulate the other component, like the water in the soil that is almost to here, evaporation, snow. And now from satellite, we have this kind of new observation that we didn't have in the past. What does it mean? That now our modeling approach can be improved a lot. But what is the reality is that actually we have done these kind of things for poor catchments. 70,000 square kilometer for me is huge, but if you look at the Po Valley in the world, in the global scale, actually it's just 1 point. And if you need to do these kind of things everywhere, it's really challenging, because actually we need to test our system everywhere with very detailed data, and also mentioned by Adam, basically this is really the problem is really in the details. So for instance, just an example here, previous model without including irrigation, and the new model including irrigation. Green line is the observation at the outlet of the catchment. This is basically, the green line is what we in hydrology want to simulate. The red line is the modeling without irrigation, and the blue line is with irrigation. Of course, we see that during dry years, we are able to simulate river discharge much better. But the point is that actually we are simulating river discharge much better. Actually, you don't see because it's here, but much better also for the flood, during the flood events. Why? Because our modeling now, including irrigation, is closer to the reality. And basically, when you don't have irrigation, you try to calibrate the model. Basically, the model is the parameters of the model were calibrated wrongly, because basically they try to accommodate a process that is not there. Consider that many modeling systems that are working at continental scale or even global scale, they don't include irrigation at all. And so basically they face this major issue. But then with satellites, for instance, we can do very nice things. For instance, here is 1 kilometer scale Europe for 2017 and 18 in Europe, and you can see that basically it changed completely the pattern of dry areas in the 2 years. So basically also to predict what is going to happen is quite complex. But the problem is here that you have a lot of black areas, because actually we cannot see most of, for instance, in this case, from space everywhere. And so what can be the role of AI can be gap filling. So this is a guy a very nice guy which I'm collaborating with. Basically, they did the gap filling of the data quite quickly with AI techniques. But then actually what you see in the gap filled area, is it really information, or is look like probably just a topography? This is something that we need to explore, because now if you look at the literature, there are plenty of papers in which we say, okay, we are simulating something at 10 meter resolution, 100 meter, kilometer scale, but nobody is going to check this data. And this is something that we as scientists, of course, we have to do, but everybody should be aware of that, because otherwise we have the wrong impression that we are now able to make, I don't know, simulation of what is going to happen in my farm, in my field, if I have a farmer with respect to the closer field, but it is not the case. We are able now to predict, we have computers that are able to predict kilometer scale something, but it doesn't mean that it's really good prediction. It might be, but it might be not. This this is one example for SunMosto, because as I mentioned, is my main field. On the left side, average SunMosto for 7 years. On the right side, the same from the modeling, from the state-of-the-art modeling from EC and WF, the best that we have. That you can see the two maps should be the same. It's just the long-term average. It's not a prediction over time. Just they're quite different. The map on the right is basically reflecting the land use and soil that they use into the modeling, into their modeling system, but basically it doesn't reflect at all what we see from satellites. This is just a single example, so the spatial patterns of the data and of the modelings typically are very different. What are the future? Basically, the only things that I want to say here is that basically we have new satellites that are going to be, for instance, couple of satellites are going to be, one of them has been already launched, the NISA satellites for high resolution SunMosto, but also another one, and the other one are scheduled for the next 2 to 3 years. So basically in the near future, we are expected to have better satellites with better capacity, and so basically the system is continuously improving. But then actually the problem is that we should be able to use all these data very efficiently. And the last challenge is to make the people aware of what we are doing. This is an initiative from WMO and all these people, all these institutions here, to basically to develop training and capacity building of all these things to the stakeholders. The two main focus here today are flood and droughts, but really making this happening is now they are working since the last 3 or 4 years. Many people have joined the system, but still to make really the use of this new technology to the stakeholders is a very long-term task. With that, this is my last slide. You can see my contacts. If you have more questions, you can happy to answer. Hope I have saved some time.
Take 2 questions.
Good afternoon. Thank you very much for the interesting presentation, Paul Cushion. My question is more about practical application. You've now got access to satellite data that is easier to compute potentially with the digital twin. Modelling floods is obviously a dynamic system, and it's not just a function of weather, but there's been so much development that's gone on. Inevitably, the nature of the land in many cities is very different from what it was before, and there's either infrastructure failures where drainage and other things haven't been built, or it's in every city's advantage to build more and more properties to tax residents that live in there. And local councils or governments don't necessarily see the infrastructure that is required to support those houses. So given some of your research is being funded by the EU, I would be interested to hear from your side how engaged they are with you in terms of either leveraging satellite data to say, well, 80% of your land mass in the city now can't ingest rainfall, so you've got a whatever percent increase of flood risk, rather than just modelling the climate change side of the equation, and how you engage with them essentially to help essentially push them forward into proactive action to address those shortfalls that have probably built up over the last 20 years or so.
Yeah, long question, and also the answer should be long. But the main point here is that 2 points. From one side, we have an initiative like also shown this morning, very nice simulation everywhere, kilometer scale. I don't want to say something very bad, but actually it looks fake if you look to use this data from people actually using the data. Stakeholder, for instance, engagement of stakeholder. I am a hydrologist, so basically I am not an expert in remote sensing. So my main topic is really to make flood system for flood prediction, drought prediction, and slide. In my region, Umbria, small region in Italy, to make our modeling system to be used by stakeholder there, that were my previous colleagues, so basically they are very expert. It needs 5 years for one single application of the modeling in very small region. And they are starting to use remote sensing data, but are starting to use. And we have a really very long engagement with them. The problem here, how to make this engagement for everywhere, it's really is something that basically probably needs much more people than we are, because actually everything that we want to make is very local. And if you look at the flood prediction, it's always a local problem. And basically people doing really stakeholders engaging in flood modeling, it's very hard that it looks at the global system or Europe or continental system, because they have their own system, because they know their own territory with all the things that you also mentioned. It's a long-term task to make all this data really used by stakeholders. And really needs a long of engagement, which means that they have to trust on what you are going to propose to them.
Yeah, I mean, the narrative that you see in the news is it's climate change that's causing flooding, so it sort of negates accountability in some ways from some governments or local councils. I just thought with advances in computing power and access to satellite data, you can potentially model that change or risk factor that previously wasn't feasible, maybe.
We can do better, but not perfect.
Yeah. Thank you.